And this happens to be an example that, has financial incentives. So, I already showed you Netflix, and, where in an example where Netflix got it completely wrong for me, and, I almost canceled my Netflix membership. Now imagine there are 100 Netflix users, and we each pay $10 a month, and if Netflix can convince us to keep our membership 1 month longer, just 1 month longer, that's 100 million times 10, $1 billion. Okay. So you can clearly see that it's in Netflix's interest for me to not cancel my membership as long as possible, and for all the other, whatever, 100 million customers. I don't know if it's 100 million, but whatever it is. Okay. And it's going to keep me as a customer longer if it can convince me that, there's a lot of stuff there for me to watch. And it can convince me that there's a lot of stuff there for me to watch if it can continuously produce movies that I would like to watch. So Netflix would like to predict how will a viewer rate a movie, in particular me. Okay. Why? We just said, because in that way it can improve the movie recommendations it gives customers. Customers think that Netflix is this great place with all these movies that they like, even though they don't see the other movies they don't like, and so they continue to be members. Okay? In fact, on this particular issue, Netflix was willing to put money where its mouth is and offered $1 million for just a 10% improvement in its movie rating system. You can think that, this is perfectly justified. If a 10% improvement in my recommendations causes me and another 100 million people to stay 1 month longer, well, that's $1 billion at stake. So $1 million is nothing. I'll offer $1 million. And the fact that they offered $1 million suggests that probably they were thinking $1 billion is indeed at stake. Okay, so this is a real problem. Okay, and the question is, how do we solve it? Okay, and you can think back to the story of the 5-year-old who looked at data when I'm discussing sort of the approaches or discussing the setting of this Netflix problem. Okay, so point number 1. There is something that we could consider to be a viewer's taste. Okay, some kind of a profile of a viewer. I like comedy, I like action, I like blockbuster movies, I like movies with lots of, good sound and lots of good-looking actors or actresses, what have you, right? I have a profile. So the way you can think of that is there's a vector, there's a vector of attributes, okay, that represents me as a viewer. Now those same attributes, for example, the fact that I like comedy, okay, can be matched to whether or not a movie has a high comedy content. Okay, so there's my viewer taste, which is described by a set of attributes, like how much do I like comedy, how much do I like action, and we can correspondingly assign to a movie how much of each attribute does the movie have. And it is reasonable to expect that, if you knew a viewer's tastes and if you knew a movie's content with respect to those tastes, then there should be some magical formula that you can use and convert that into a single number, which is how much do you think that viewer would like that movie. Okay. So let's call this magical formula a pattern that relates viewer taste and movie, content to how much the viewer would rate that movie. Okay. Now, we don't know what that formula is, because if we did, or for example, if Netflix did, then they wouldn't need to put out this $1 million prize. So we don't know what that formula is. Okay. So just like the child who doesn't know what's the definition of a tree, Netflix doesn't know how to specifically write down a formula that converts a viewer taste and a movie content to a rating. But just like the child who has lots of pictures through their experience, or lots of experience of looking at things that have been told to them as being trees, and looking at things where they have been told those are not trees, Netflix has a lot of data. And, what does this data consist of? This data consists of a viewer comes along, having watched a particular movie, and rates it. Okay. So even though Netflix doesn't know exactly how to define or compute a viewer's taste and doesn't know what the magical formula is that connects taste plus content to rating, Netflix has a lot of data in which viewers have told them the rating, which indirectly, in some sense, gives information about how their taste has interacted with the movie content. Even though we don't know the taste and we don't know the movie content, we know the interaction because the viewer rated that movie. Okay, so we have a lot of data. And then the question becomes, can we reverse engineer that data? Okay, and that is where the learning comes in. Can we reverse engineer that data and back out what exactly a viewer's tastes are based on all the movies they rated? Okay, and what exactly is the content of a movie based on all viewers that rated a movie? Okay. If we can back those out in a way that's consistent with all the ratings that we have observed, okay, then we have obtained the first step in predicting a viewer's rating, which is for each viewer we will know what is their taste vector, and for each movie we will know what is its content vector. Okay. Now that entire process is complicated, and we can discuss sort of methods for doing this, which is sort of this bilinear model, and we'll discuss the linear model later. The bilinear model, which was used to win this competition, is very similar. Okay. But instead of getting into the details of exactly how this problem can be solved, I want to extract high-level details. Okay. And the most important high-level detail here, is that there is some pattern, there is some formula, there is some relationship between a viewer's taste and a movie's content and the rating that they would give to that movie. Okay. So this pattern is fundamental. Okay, so this pattern exists. So there's a pattern, it exists. There's some pattern. Okay. We don't know it. Okay, because if we did know it, we just implement it and we're done. Okay. And just like with Netflix, we have a lot of data to learn it. So this is now going to be our class model. And why is this going to be our class model? Because this is exactly the situation in which machine learning applies. Okay. So there is some pattern that exists. Okay. Because if there's no pattern that exists, then there's nothing to learn. Okay. We don't know it, because if we did know it, again, there's nothing to learn. Okay. And there's a pattern, we don't know it. At this point, we're stumped. And the only thing that allows us to make progress, short of giving us the pattern, is give us some data that has somehow in it embedded, sort of indirectly, the pattern. Okay. And then the machine learning task is to reverse engineer. Okay, is to reverse engineer the data to extract the pattern. Okay. And then why do we care? Well, it's not the reverse engineering of the data to extract the pattern that's important. Netflix doesn't care about the pattern. What Netflix cares about is when I or some other user logs into Netflix for the next time, okay, it's going to compare my viewer taste with all the movies it has available and make a set of recommendations to me. That's what Netflix cares about. Okay. So while yes, it's nice that we have data and we're going to try to reverse engineer the pattern, and it would be nice to know the pattern, at the end of the day, I don't really need to know the pattern. All I need to know is for this viewer, what will they rate that movie? Okay. And so that's how I'm going to test myself. I'm not going to test myself by, how nice is the pattern that you extracted from the data? How aesthetic is it? How, compact is it? How reasonable is it? We don't care about the pattern per se. What we care about is the performance of the pattern, or whatever pattern we think we have extracted, on some new test case. The test case being me arriving and you showing me another movie, a movie that you think I would like. Okay. So that's a fairly complicated problem. The solution is fairly complicated, but it has these three ingredients. There's a pattern, we don't know it, we have data to learn it. Okay. Let's simplify more and get to an even more concrete problem. And this problem will be concrete enough that we can use it as a template to pin down and extract the main players in this sort of machine learning game, which corresponds to this high-level class model of a pattern exists, we don't know it, we have data to learn it. Okay. And that is credit approval. Okay. So It's a very conceptual example, it's a very concrete example, but it'll help us to crystallize the issue. So here's a think of this as somebody who's graduated from college, had a job for, let's say, 10 years, so 32 years old, male, salary 40K, is 26K in debt, has been in his current job for 1 year, has lived at his current residence for 3 years, and so on and so forth. These are the kinds of questions that a typical credit card application or a loan application will get from you. Okay. Now, here's the question. Do you approve for credit or not? So you're a banker. Do you give this guy 15K credit card or not? A very simple question. The answer is yes or no. Okay, and some people might say yes, some people might say no. But at the moment, we're not going to focus on what the correct answer is. At the moment, we're focusing on there is some magical formula that could take this input and output the correct answer. In other words, it's not a random guess whether or not you should approve this guy for credit. Okay, it's not a random guess. There is some relationship between these, input attributes of an applicant and whether or not you should. So there's some pattern. There's some magical formula. We don't know it, because if we did know it, we wouldn't even be discussing. The banks would all have implemented it. They'd all be assigning credit perfectly. Nobody would default on debt, and so on and so forth. Okay, so we don't know it. And banks have a lot of data. So they get, many applications for credit a month. Some of them they reject, and some of them they accept. And then of the ones they accept, some of them pay back the credit, and some of them default. So there's a bunch of people they've rejected, there's a bunch of people who've defaulted, and there's a bunch of people who have been good, fine, upstanding credit card holders. Okay. So from this data, could we reverse engineer the magical formula that links an applicant's attributes to whether or not they should get that credit card? Okay. Now, again, we don't care about that formula. All the bank really cares about is, when the next applicant comes, I'm going to use whatever formula you reverse engineered to say yes or no. And the only thing that matters is, was I right on that test applicant? Okay, so to summarize, we have these attributes of an applicant. We don't know a magical formula for approving credit, but we know that it exists. Okay, and banks have lots of data. So we can try to learn this formula. Okay. Think back to the 5-year-old. There is some magical formula / pattern that when you look at a picture, if it contains a tree, the picture will have a particular pattern, and if it doesn't, it will not have that particular pattern. So the pattern exists. But the 5-year-old doesn't know what that pattern is. The 5-year-old doesn't know the definition of a tree. Okay. But the 5-year-old has a lot of data based on, 5 years of growing up with people telling her what is and is not a tree. Okay, and the 5-year-old has managed to reverse engineer that data and produce a representation in her mind of what the pattern is that constitutes a tree. And then the 5-year-old has used that pattern. Whether or not the pattern is right or wrong is irrelevant. The 5-year-old used that pattern to identify the trees in the picture and got them all right. So we don't even care if her definition or her internal pattern of a tree is right or wrong. What we care about is she got all her tests correct. Okay, same thing here. Reverse engineer the pattern, but I'm not really interested in the pattern. I'm interested in whether you're going to get the next credit card applicant correct or incorrect. Okay, so that's the setup. Machine learning is relevant when you know that there's a pattern that you're trying to learn. You don't know the pattern, otherwise you wouldn't be trying to learn it. Okay, and you need some way to learn it. Okay, you can't learn it from a vacuum, so you have data. And really, in most practical situations, pattern exists and we don't know it. So the crucial aspect is the data. So if someone comes to me and says, here's a fancy machine learning problem and blah, 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 and look at how interesting it is and how cute and so on. I say, okay, great, yes, but if it's going to be a machine learning problem, what data do you have? That's the first question you ask. Do you have data? If you have data, let's talk. If you don't have data, you need someone else's help. Okay, now if you have data, then Are you sure that there's a pattern? Are you sure that there's a relationship between what you can observe, like a credit card applicant's features, okay, and what you're trying to predict? If there's no reason to believe there's a relationship, then again, I'm not your guy. But if you think there's a relationship, you have the data, okay, then let's talk. Okay, now let's pin this down mathematically, and I want to, in the process, also show you the other mode in which I'm going to be presenting material to you, which is sort of a blackboard lecture. Okay. So what we're going to do is we're going to now, within the context of this credit approval, we're going to extract the key players, and those key players are generic to any machine learning problem.